All right, this is one of the graphs I'd like to use a lot on the AP exam, so let's focus on this. A mass spec is a machine that they run elements through to figure out the different masses of the different isotopes. Keep in mind, like for example, if we have copper here, there's two forms of copper. There's copper 63 and copper 65. Copper has the same number of protons, but the difference in the isotopes is the different numbers of neutrons. So if you notice here, 63 and 65 represent the different mass numbers, which is going to be ultimately protons plus neutrons here, protons plus neutrons here. The y-axis of the graph represents the total number of atoms, or the relative number, the percent abundance basically. As you notice, 63 is a lot higher. In fact, it comes up at 69%, then 65, which comes in at 31%. That's how we get the average atomic mass on the periodic table for copper is 63.54 AMU. That comes from the idea that the majority of copper, or 69, if you take the mass number 63 times 0.69, that'll give you the percentage of that, plus mass number 65, which has a percentage based on the mass spec, or running the elements through, the atoms, is 31. Ultimately, that gets me that. So when you're looking to answer questions based on this is going to all be focused around isotopes, and the key difference is the different number of neutrons, not the number of protons. So if you look here, they talked about elements I and tellurium, and they think that it was believed to be a mixture of I and Te. And then they're asking you, well, what would, all the statements are true, which one would be the basis of concluding that the sample was pure Te, meaning there was no I? Well, if I look down here, notice how it tells me I have iodine consists of only one isotope with 74 neutrons. First thing I'm going to do is check the periodic table and realize that its atomic number is 53. If I had 53 and 74 together, it's equal to 127. That's my mass number. Notice how there's nothing in the bar graph right there, missing. It's empty. That tells me that that is the reason why you know that it was only Te. Because the only thing really shown on the graph is mass number, and mass number comes from the number of protons plus the number of neutrons. So since they give you the neutrons here, they expect you to go and get the protons from the periodic table, add them together, and that would have been 100% if it was only one isotope. Anything to do with this is going to be centered around isotopes, different forms of the element with just different numbers of neutrons. Next one. Silicon crystals are semiconductors. Semiconductor basically is used in phones, computer chips, everything else. There's basically two types of semiconductors. There's a p-type, which we call positive, which basically a positive form of semiconductor, which is you're adding elements from group 13 like aluminum, which has one less valence electron than silicon, because silicon's in every semiconductor, right? So you're either going to add something that has one less valence electron, or an n-type semiconductor is where you add an element from group 15, for example, phosphorus. Group 15 means they have an extra valence electron. With the extra electrons, it means it makes it easier to convert from something that doesn't conduct electricity very well to something that does. Ultimately, when they talk about the fact that which of the following is correct reason increasing conductive Si crystals when a small fraction are replaced to those with a different element, notice that really Ge is from the same column. There's no difference in valence electrons, so that reason, and some of these are untrue anyway, is why these wouldn't be considered for semiconductors. When you talk about semiconduction or any kind of conduction, it's not about positive charges or protons, it's about mobile negative charges, or basically electrons. So by adding phosphorus, and you're making an n-type semiconductor, which you don't really need to know that much, but ultimately you need to know that you're adding electrons, which makes something more of a conductor, a semiconductor. Just so you know, a normal conductor has what's called a conduction band. Think of it like on the freeway when they have those high occupancy vehicle, the HOV lanes, right, where you can drive with less traffic. The conduction band is basically where the electrons pop up into, like in something that conducts. The electrons can easily pop in the conduction band, and then they get taken wherever they need to flow. In a semiconductor, there's a gap between them. There's what's called a little band gap. So the way a semiconductor works is if you increase temperature, you can cause the electrons to pop up into the conduction band, and then the more energy you add, the more electrons you can cross this gap, which allows it to get into the conduction band. That's why it's a semiconductor. So if you increase the temperature, you increase the conduction. An insulator, which has no conduction, the reason why something's an insulator is the gap between the two levels is too high. You can't add enough energy to cause the electrons to get into the conduction band. So the term semiconductor and chips, phones, all those things work on the idea that you can take electrons and pop them up into this conduction band. They might ask you something like that, so there you go. Next, chromatography. We didn't do a chromatography lab. The only key thing you need to know about chromatography is it's used to separate out components in a solution, like dyes and stuff like that. So you can take a dye and separate it out. It's based on the idea of intermolecular attraction. Stationary phase represents the paper, so we use special chromatography paper, and the solvent is the moving phase. Basically what happens is you decide whether or not the dye has a greater attraction to the paper or to the solvent. It's either the affinity, we call it the affinity. So the greater affinity to the solvent or to the paper. We calculate, or you can calculate, what's called an RF value, which is a retention factor. And the formula for a retention factor is the distance traveled by the component of the mixture and the distance traveled by the solvent. So you would soak something like a paper with dye, let's say. You had a little dye on here. Put a little dye here. Component of the dye, and it was made of 3 different colors or 3 different parts, right? So one travels up to here and stops. Another color, we'll say red, makes it all the way up to there. And finally blue makes it all up to there. What can you tell? Well, basically, the greater the distance traveled by the different components of the dye means the greater the attraction to, let's say if we were using alcohol, the polar substance. So alcohol would be the solvent we would use. You put a little solvent here in the alcohols, it would go all the way up to the top. That's the line of the solvent. To calculate out the retention factor, it would be the distance traveled by the component in the mixture divided by the distance traveled by the solvent. So the solvent here, basically the greater distance it travels, the greater the attraction basically to the solvent versus the paper, which is usually basically nonpolar. All right, another graph that I think they're going to use, or they use a lot on the AP exam, is this one. This graph basically kind of shows you where nonpolar covalent bonds, the idea where they come from is. The idea is you're minimizing the potential energy between the atoms. And what you're doing that is they can't get too close because then the nuclei would start to repel each other. So the idea is in this graph is this is basically you reach an area of what's called minimum potential energy. It minimizes the amount of potential energy, and at that distance, what we call the internuclear distance, is this distance the nuclei would be too close. This distance the nuclei would be too far apart. So what happens is you want to get to a point where you minimize the potential energy, and this is really applying to nonpolar covalent bonds. So the idea is the distance that nonmetals form when they form nonmetal covalent bonds is related to the internuclear distance to have the lowest potential energy as possible. Number 9, I barely touched on this in class. The idea of calorimetry, whenever we do calorimetry, has to do with thermodynamics. If you take something and you drop it in water, like let's say we do a reaction like when you're doing your hand warmer lab, you would drop something in water, and then what would happen would be possibly, if it's exothermic, the energy, for this case they were taking a metal. They took a 100 gram piece of metal, and what they did was they dropped it in water, and then what happened was the heat went from the metal to the water. The great assumption we make in calorimetry is what happens to the water, so the temperature of the water is going to go up. So delta T is going to go up for the water. So we would say its Q for the water would be positive because it's gaining heat. It's gaining the heat that metal is losing. They're going to change. They're not going to change to be the same temperatures. The metal's at 100 degrees. The final temperature of the water is 35. So the water goes from basically starts out at 22 and goes up to 35. The metal starts at 100 and drops down to 35. The difference has to do with the difference in specific heats. The fundamental idea of calorimetry is what happens to the water, in this case gains Q, heat, is the opposite of what happens to the reaction or whatever we do in the calorimeter. So that's why B is the correct answer. The metal changed more than the water did, but the metal lost the same amount of thermal energy as the water gained. That's the idea of the Q of the water is equal to the Q of the reaction that we do, and that's a fundamental idea of calorimetry. Next thing, we were talking about alloys, and they had a question on there about alloys. Remember, alloys are basically where you take two metals and you combine them, and supposedly, or what it would do is basically make it a little stronger. There's two kinds. There's a substitutional alloy. Substitutional alloy is the constituents, whatever the atoms that they're adding in, are roughly the same size. So the idea when it says substitutional alloy is the size is about equal. Okay, so it fits in the lattice structure of the metal ions. Interstitial alloy is the constituents have different radii. They're smaller, so they fit into little gaps. What does this mean for properties? We think of it like this. When they're asking you here are the properties right here. If it's substitutional, the resulting solid is pretty much malleable, ductile, and has exactly the same type of density. It doesn't really change anything. For example, sterling silver. Sterling silver is silver and copper put together. That's basically how you make sterling silver. It's a substitutional alloy because the radii with them are within roughly 15% of each other, so they're close enough in size to where it's not going to cause a difference. Interstitial, basically the commonly difference in size results in the solid being more rigid, meaning basically stronger, less flexible, and less ductile. So it's going to become more rigid, less malleable, and less ductile. So if we go back to the question here, they were talking about the two alloys, right? And they were saying each have the same fraction, but the gold-copper alloy is harder than the gold-silver. Why? If you look, the gold versus the copper alloy, or the copper versus the silver alloy, if you look here, here's copper, here's silver. If you look, the AU and the AG are relatively the same size. So that's going to be a substitutional one because it's the same size. Where this is interstitial substitution with the copper. So the reason why the AU alloy is harder is because copper atoms are smaller than silver atoms, so they interfere with the displacement of atoms in the alloy. So that goes back to this idea. Interstitial. The interstitial one is the fact that the resulting solid is more rigid, less malleable, and ductile. Okay? If you remember this is a PES diagram. What this represents is the atomic structure of an atom. Your first thing you want to check is the energy. Which direction is the energy trend going? The greatest binding energy, or the amount of energy holding the electrons to the nucleus, Coulombic force, is related to basically the nuclear charge. The greater the nuclear charge, or the closer the distance, the stronger they're held. So if you look here, this is the most energy, which means this is my 1s shell, this is my 2s, and this is my 2p. Couple things. It'll say binding energy on the bottom, and it'll say relative number of electrons here. The height of this tells me I know in 1s there's 2 electrons. So this height, this peak represents 2 electrons. This represents 2 electrons as well. And then finally, if you notice, this peak is about 3 times the size of this peak, which means ultimately I have P2 with 6 electrons in there based on the height of the peak. I know the 1s has to be here because it's closest to the nucleus, so the electrons are harder to remove, greater Coulombic attraction, and then the energy drops here the farther they get away from the nucleus. So they asked me, peaks A, B, and C represent the energy of electrons in which subshells? Well, A is going to represent 1s, B is going to represent 2s, and C is going to represent 2p. So that would be the correct answer, and it represents neon. You know it's a sample of neon, you can tell by the height. You should be able to maybe even spot what the element is. Just start numbering from the highest 1s, 1s2, that would tell you that's the height of 2 electrons. Then you could compare all the other lines if you had to identify the element. If you look here, notice it says binding energy and it says relative number of electrons. So ultimately I know that this is basically representing 1s and this is representing 1s, and it tells you amount of energy required. Obviously the energy is higher for oxygen. So the energy is higher for oxygen than it is, if you notice, this is 400, this is a little over 500. Why? Well, ultimately there's two things. It's distance, but ultimately remember Coulombic attraction is Q1 times Q2 over R squared. First and foremost, oxygen has 8 protons in the nucleus. It has a greater effective nuclear charge. So if you're wondering about figuring out Why this is the correct answer, why is nitrogen? The fact is nitrogen only has 7 protons, therefore it has basically a less effective nuclear charge, which means then ultimately, since the charge is a little smaller, it's easier to remove the electron, and you notice that with the smaller binding energy. All right, another key thing they ask is if you had an unknown acid and you're titrating it, right, what measurements might be required to figure out the moles of NaOH used in the titration? That's just the idea. M times L always gives us moles. So you would get the volume in liters from the burette. You would read it right off the burette. You would get the molarity because it would be standardized using KHP. Write a mathematical expression that can be used to determine the number of moles of NaOH used to reach the endpoint in a titration. So then basically you would just have the M times L. You could use MAVA equals MBVB. This side will always remember at equivalence moles of the OH is equal to moles of H plus. The next question they ask is how can the number of moles of HA be determined? Once you know moles of OH, it's going to be the same as H plus. And then the next question they ask is, in the addition, what other measurements must be made to determine the molar mass of the unknown acid? When you go to find the molar mass of an unknown acid, what you do is you titrate it. You know how many grams of the acid you weigh out. So you basically weigh out a solid acid. So you have grams of HA. The way you figure out the molar mass of the unknown acid is you take the grams of the HA and you just divide by moles of H plus, found out using the MAVA equals MBVB. So M times V will tell me moles of OH, which is the same thing as the moles of H plus. So to find the molar mass of the unknown acid, I just take grams of the solid acid, I'll rewrite it here, divided by moles of H plus, I get from the titration equation, and that represents the mathematical equation. All right, the next thing I'm going to do is I'm going to go over the real quick keys to the thermochemistry problems. I did a couple of these in class, but they're important because thermo is an important subject on the test. So if you look here, problem 34, they ask you how much heat is released. So this is heat as a conversion factor, but notice this. They're asking you when Cl2 is formed. Here it's a reactant. Formed would mean it would have to be on the other side, like a product. They do that a lot in thermochemistry, especially on like a little heat as a conversion factor. So ultimately what I would have to do is flip the value. When I flip the reaction, I get positive 437. And ultimately I just take the 0.050 moles of Cl and I divide by 0.5 moles of Cl, because that's Cl2, because that's the coefficient in the equation, is equal to a positive 437. You do your calculations and you get 43.7 when you put it all in scientific notation and calculate it out. Next one. Some of you guys had trouble with this. They ask you equal masses. Whenever they tell you equal masses, the trick on the AP exam is whatever the first one is listed, you pick that as your mass. So K, if you look on the periodic table, is 39.1. So I'm going to say 39.1 grams of K is equal, and the molar mass of K is 39.1 K is equal to 1 mole of K. 1 mole of K is equal to, oh, they're asking me limiting reactant, so KCl actually. So it's equal to 1 mole of K is equal to 1 mole of KCl. Then I'm going to take the 39.1 grams of Cl2 here. Molar mass of Cl is 71 grams of Cl2 is equal to 1 mole of Cl2. Now the coefficient here is 0.5 moles of Cl2 is equal to 1 mole of KCl. When I go and do the math, 39, that simplifies. I basically get 1 mole of this. Then I go and simplify this. 0.5 of this is going to simplify to 35.5. I know that's going to be greater than 1. It's going to be 1, I don't know, 1.2 something close, something like that. So right around there, 1.2, which means this is my excess, which means this is my limiting reactant. So I know that basically K runs out. Since K runs out, when this goes to completion or as much as can be consumed, the only thing that's going to be left is KCl is going to be created and some Cl2 is going to be excess. Next problem. This was a hard problem. They asked, which of the following in the table are exothermic processes? Well, if you look, one thing I'll tell you is whenever you form an ionic compound from ions, it is an exothermic process. So we would say here the delta H of this is negative. If you remember when we studied electron affinity, whenever you add an electron to something, it's a release of energy. So this value again is negative. Now what about these? Notice how I'm going from a solid to a gas. If you use the SLG rule, going from a solid liquid to a gas, to go from a solid to a liquid you have to add energy. Delta H increases, or it's a positive delta H. Go to a liquid to a gas, same thing. So to go from a solid to a gas, the delta H value is going to be positive. Anytime I remove an electron, this is like ionization energy. I have this K atom, I have K plus. I'm removing an ion, is going to require energy to rip it off. Last thing is here, Cl2 is a gas to just Cl. You're going to break bonds. That value is going to be delta H is going to be positive as well. 37. It is observed that a reaction producing KCl essentially goes to completion. So it basically goes forward, which means it's thermodynamically favorable. Why, they say? Well, when it goes to completion, and it says thermodynamically favorable, it means that, and it tells you it goes to completion, means it's favorable. So the fact that they're saying unfavorable in B means you can scratch it, and unfavorable in D can be scratched. So then I'm down to C or A. If I look, this one says the reaction is favorable because it's driven by both enthalpy and entropy. Remember when we studied thermodynamics is that entropy, a negative delta H tends to be favored and a positive delta S tends to be favored. Well, I have the negative delta H, that's good to go. But do I have the positive delta S? If I look, I have a solid going to a solid, that's basically a wash. But I also have a gas going to a solid, which tells me my delta S is negative. So what has to be driving the reaction is only enthalpy, which is the same thing as delta H. That's why A is the correct answer. The last question on here is kind of like a Hess's law problem. They give you all this stuff and they say, well, what would the enthalpy of the reaction or the delta H for the reaction be? So I start here. I know I need two equations. I need Cl and Cl2. And if I look here, this doesn't contain it, this doesn't contain it. This has Cl, but I'm not really going to need it because of the KCl, so I cross it off. So I have to manipulate these two equations. When I look, it says I need 2Cl minus. Notice I have Cl minus right there. So according to Hess's law, to get this to 2Cl minus, I would multiply that by 2, 2, and 2, which would ultimately give me 2y. Then what I need to do is, if I look here, ultimately I get 2 Cl's and Cl2. 1 Cl2, I have the 1 Cl2 already, correct side, correct coefficient, I'm good to go. So ultimately, what do I have to do? It would be x plus 2y, because it's Hess's law, would give me the value I need for enthalpy. So it's all that is a Hess's law problem. All right? Now, that is it. I wish you the best of luck. I know you guys worked really hard all year long. I appreciate all your hard work, and I know you'll do well on the exam. Get some rest. Try and go to bed. The rule is on Sunday at 11 o'clock, you need your rest. Go to bed.